It is my pleasure to introduce our next speaker, Isabella Laba. The title of her talk is On the Minimal Period of Integer Tilings.
Thank you very much for the invitation. This is going to be a talk about some joint work with Dima Zakharov. It's from a couple of years ago, but it makes for a good introduction to this topic, so that's what I chose for this conference. So let me start with the basics of integer tilings. Here's what we mean when we say that a finite set tiles the integers. Let's say that A is a finite set, a subset of the integers. We say that A tiles the integers by translations. If we can cover the integers by a union of its disjoint translates. So in other words, there is an infinite translation set. Let's call it T, so that every integer can be represented uniquely as a sum of two elements, one from A, one from T. Here are a couple of examples. The set 0, 2 tiles the integers in the obvious way. You can place 0, 2 at 0 and 2, then a translated copy of it at 1, 3, and then start the next copy at 4, and then continue the pattern. You can do the same with the set 0, 4, 8. You place the next copy of A starting at 1, and then you get 5, 9. You fill up the interval, and then you move on. If you take 0, 1, 3 instead, then that does not tile the integers because there is no way to fill the gap between 1 and 3. We're going to be interested in the periodicity question for that type of tilings. It is a well-known fact that all tilings of the integers by a finite set are periodic, so that the translation set has to be a direct sum of a finite set and an infinite arithmetic progression. This reduces the problem to tilings of finite cyclic groups with addition mod m. This is an old result due to Newman, but there's an interesting question about minimizing the period, and that's what I'm going to talk about today. Before we do that, I want to mention one more reduction, which is that if I have a finite tile A, then the period of that tiling could be, I don't know a priori what it's going to be, but if I know that A tiles the integers, then I can also find a tiling whose period has the same prime factors as the cardinality of A. It always has to be divisible by the cardinality of A for obvious reasons. The less trivial reduction is that I can also make sure that there are no prime factors that do not already appear in the cardinality of A. Something that I mentioned briefly is that tiling complements are not unique, so that the same set can tile the integers in many ways. For instance, if I take the set 0, 10, 20, then I can do the interval filling sort of thing. I can place another copy of it at 1, so then I get 1, 11, 21. Then 2, 12, 22, and continue the pattern, and that fills an interval of period 30, an interval of length 30, and then that gets me a tiling of period 30. But I just said that there should be a tiling whose cardinality should only be divisible by prime factors of the cardinality of A and no other primes. So if we look at it more carefully, then A here is also a complete set of residues mod 3, so that it actually tiles the integers with periods 3. It's maybe a little bit obvious from just looking at it, but it also works. So we're going to be looking for a minimal tiling period. I want to clarify that this question can be understood in two different ways. One is given a specific tiling, a plus t is equal to z. What is the minimal period of that particular tiling? So I'm given a tiling. I want to find the minimal period of that. The other question is, if I'm given an A that I know tiles the integers, what is the minimal tiling period among all possible tilings of the integers by that set? So for the set from the last example, if I look at the first tiling of period 30, then 30 is the minimal period of that tiling. I cannot make it smaller. But if I minimize over all possible tilings of the integers by A, then the minimum would be 3. That's given by the tiling in the second bullet point. And I cannot make it less than that because I cannot have a tiling of period that's less than the cardinality of A. So I want to clarify the distinction between those two questions. Now, here are a couple of answers. We do not know the full answer to either question, but there are partial results. The first one goes back to the work of Newman that I mentioned earlier. A pigeonholing argument just based on looking at all possible configurations by configurations of elements in the interval of length equal to the diameter of A. So D is going to be the diameter of A here in this talk, and that's the maximum of A minus the minimum of A. So the pigeonholing argument gets us a bound on the period of any tiling, and that's going to be 2 to the D here. There have been improvements by Kolantzakis, Ruja, and then the current best bound is due to Biro, which says that any tiling of Z by A has period at most exponential in D to the 1/3 plus epsilon, and that's for large enough diameters. It's possible that this could be improved. We don't know yet. The lower bound, the best one that's known so far is that there exist tilings of period at least something that's less than Biro's bound, but it's still a super polynomial. And that's due to Steinberger improving on an earlier result by Kolantzakis. In this last example due to Steinberger, and also in the example due to Kolantzakis, the tiling period has prime factors that the cardinality of A does not have. So the result that I proved with Zaharov is kind of in two parts. Assume that A tiles the integers, and let's use D to denote again the diameter of A. Then an upper bound is that A admits a tiling of period at most something like e to the log squared D over log D. And this is actually true for any tiling where M has the same prime factors as the cardinality of A. From the other end, if we assume that A and M have the same prime factors, so we do not introduce any prime factors into the tiling period that do not already appear in the cardinality of A, we can still get tilings of period at least about D to the 3/2. You might have noticed some similarity between the upper bound in my result here with Dima and the lower bound from Steinberger's work. So I want to clarify upfront that this is basically not quite a coincidence, but also there is no reason to think that either bound would be optimal. The reason why we get the same expression is that we use the same estimate on the number of primes less than a given number. And that's why we get bounds that look similar. But also we address different questions, and our bound is not really related to Steinberger's construction. We construct a tiling that keeps only the prime factors of A. Steinberger introduces a lot of them. So there is no reason why either estimate should be optimal in its context. Some basic tools that we use in the proof are the Chinese remainder theorem. So this provides a geometric representation of the problem. We use mask polynomials, and we also use cyclotomic polynomials. So let me tell you a little bit about those. Starting with the Chinese remainder theorem, let's say that we work in a cyclic group Zm. I already said that we can reduce tilings of the integers to that setting. If M is a product of prime powers pi to the ni, then we can represent Zm as a direct sum of the corresponding cyclic groups of prime power order. And geometrically, that represents Zm as a d-dimensional periodic lattice with multiple scales. And it is important that the periods in different directions are powers of distinct primes. So the picture that we want to keep in mind is sort of a multidimensional lattice, three-dimensional in this case here in the picture. And the sets I indicated in yellow are two arithmetic progressions of different steps. So in the geometric representation, these would be sublattices. In that representation, if we are given a tiling of period M of the integers, that translates to a tiling of Zm by two finite sets. And that then translates to a tiling of the d-dimensional lattice with the periodicity conditions that I noted. I want to start with a special type of integer tilings that can be constructed as follows. We can start with a set that in the Chinese remainder theorem coordinates can be identified with a discrete rectangular box. So you kind of take an arithmetic progression like here in the picture on the left, and then we kind of translate that to a rectangle in the corresponding Euclidean space of the same dimension. So for a two-dimensional box, we get a two-dimensional rectangle. And then we can use that rectangle to tile a bigger rectangle as shown in the picture in the trivial way. But then one thing about that is that rectangles actually allow other tilings. So I could use the lattice-based tiling, but I could also construct more complicated tilings by shifting columns. So, for example, the tiling on the left was obtained by first tiling the plane with rectangles aligned in a lattice, and then I shifted the columns of that lattice, possibly by different increments. In a three-dimensional picture, so that would correspond to three distinct prime factors, I can again start with a lattice tiling, and then I can shift columns in all three directions. And if I only shift selected columns, like shown in the picture on the right, I'm going to be shifting the three columns with arrows next to them, one vertical, one horizontal, and one sort of transversal to the screen. Then I can do all three of those. So that lets me construct more complicated tilings in higher dimensions or in the integers with more prime factors. That type of constructions go back to the work of Sabo, who used that to disprove certain conjectures on group factorization. The same idea was used in the constructions of tilings with long periods. The set is a discrete rectangular box, so it actually admits a tiling with period equal to the cardinality of A, but then we can mess it up using column shifts to make the tiling more complicated, and that also increases the period of the tiling complement. The tiling in the constructions by Kolontzakis and Steinberger has the additional prime factors. Geometrically, it means that A is not a full-dimensional rectangular box. In my work with Zakharov, we do not introduce additional prime, but also the quantitative estimate is weaker. To say a little bit about the upper bound, I need to introduce cyclotomic polynomials. The S cyclotomic polynomial is the minimal polynomial of the S roots of unity. These can also be defined inductively by factoring x to the n minus 1, and then the irreducible factors are going to be the cyclotomic polynomials. So just to give you a simple example, x minus 1 is going to be phi 1 because that's the only irreducible factor that that's going to have. If I factor x squared minus 1, then I have two factors. X minus 1 was phi 1, so the other factor has to be phi 2. If I factor x cubed minus 1, that gets me phi 3. To get phi 6, I need to factor x to the 6th minus 1. That gets me phi 1, phi 3, phi 2, and then one other factor that's going to have to be phi 6. So that's how they come up. The polynomial formulation of tiling that we're going to need is in terms of the mask polynomials of A and B. So given A and B subsets of non-negative integers, I can define the corresponding polynomials A of x equal to the sum of x to the A, where the exponents are elements of A, and likewise for B. Then the tiling condition is equivalent to saying that A of x times B of x is equal to the polynomial I wrote here. And this is by just multiplying out the polynomials and looking at the exponents. And then if I remember that the polynomial, that the cyclotomic polynomials are exactly the irreducible factors of the polynomial on the right, then I can state the tiling condition in terms of those. So each cyclotomic polynomial, whereas divides m and is different from 1, has to divide at least one of a of x and b of x. So let's recall the result that I'm trying to prove, assuming that d is the diameter of A. I want to, I'm given a tiling A plus B is equal to Zm. I'm also assuming that M has the same prime factors as A. And then I want to prove an upper bound on the minimal period of that. One thing I want to note is that M does not have to be less than the minimal period I stated here, but if it is larger, then this means that the tiling actually has a smaller period that I can identify. So the main step is as follows. Suppose that I have a tiling with minimal period M, so I'm also going to assume that. And then I can prove that for every top power of every prime in the prime factor decomposition of M, I can identify a cyclotomic polynomial so that phi s divides A of x, and that prime power divides S. Basically, if I could not do that, then I would be able to use the factorization from the last page, this one here, to identify a smaller period of the tiling, and then I could work with that. So this is the key result in the proof. And that gets us a lower bound on D. D in terms of the polynomials of A of x and B of x is going to be the degree of A of x. And the result here on top gets us a lower bound on that in terms of those prime powers pi to the ni. And then if I combine those, I get that the period is bounded by 2d to the d. And then together with the bound on the little d, that's the estimate on the number of primes less than a given number, the estimate that I mentioned earlier. That gets us the bound that we want to prove. I also want to mention a connection to something called the Cohen-Meyerowitz conjecture. This is the kind of the main conjecture about integer tiles. There are two conditions that are kind of conjectured to be true for all integer tiles. This is known for some cases, but it's not known in general. I'm going to skip those and just mention the connection here. So in one direction, if A tiles the integers and satisfies those conditions, then it also admits a very regular kind of structured tiling that was explicitly constructed by Cohen-Meyerowitz. And then the period of that tiling can be computed explicitly. And then if we assume further that the condition is satisfied, then that period is at most 2d. So that's much better by many orders orders of magnitude than any bounds that we can prove so far. Okay, thank you for your attention.
Thank you. Is there any question to the speaker? If not, let us thank the speaker again. So our next talk will start at 2 p.m. US Central Time. See you then. Bye, everybody.